Welcome to the final webinar of the academic year, the final Next Generation Science Standards webinar. We focus primarily on NGSS and the Earth and Space Sciences. However, we recognize that when people are building curriculum and bundling performance expectations around a topic, that those often end up cutting across disciplines within the curriculum. So today we're focusing on resources that are being made available by professional societies and organizations, which can show examples of how things can run across the curriculum. I'm Susan Sullivan. I'm director of the series Education and Outreach Program and moderator of this series. I'm joined on the line today by Aleeza Oshry and Ed Robeck and John McDoris, who have also been part of the organization of this webinar series. Before we get started, I want to introduce you to our presenters. We're joined today by Dr. Ellen Roseman from AAAS, the American Association for the Advancement of Science. And Ellen is director for Project 2061 of AAAS, where she's worked on increasing science literacy since 1989. And in that role, she is responsible for overseeing all of the project's programs and activities in curriculum, instruction, and assessment. Jim Kessler is currently manager of the K-8 Science Office in the Education Division of the American Chemical Society. He was the editor of Wonder Science Magazine, a physical science activity magazine for elementary teachers and students. And he's co-developer and co-author of the book and website Inquiry in Action, Investigating Matter Through Inquiry, and another website for middle school chemistry, Big Ideas About the Very Small. He'll be introducing the American Chemical Society Middle School Chemistry Resource. Our third presenter is Aleeza Oshry. She's a Science Education Fellow at the Howard Hughes Medical Institute. She has a wide breadth of experience in science education, teaching, and developing curriculum for secondary through college-level courses and for other service providers. She focuses on the Maryland Environmental Literacy Partnership and developing curricular resources to support the first national environmental literacy graduation requirement. Aleeza will introduce a planning guide for implementation of NGSS developed through her work at HHMI. Okay, I need to get back to where I was. Here we go. I'd like to draw your attention to some upcoming events. So this is the last webinar of this academic year, and it will be archived so that you can go back and look at it again, or you can share it with your colleagues, whatever's useful to you. You will get that link after the webinar when it's posted. And also, there are a couple of other opportunities coming up. August 1st is the abstract deadline for the Geological Society of America meeting, and there we are organizing a session called Getting It Done, Experiences of Implementing the Framework in NGSS and Earth and Space Science. So this is a pretty nuts and bolts in the trenches opportunity to share what's been working, share lessons learned, and just help each other get it done. July 17 through 21 is the Earth Educators Rendezvous in Albuquerque, New Mexico. There we will host a roundtable discussion of the same name, again with the intention of helping each other share our experiences and build more community around this topic. You can sign up for the email list and see archived webinars, see those links when they come out at this link. And we would welcome you to sign up for the email list there, or let any of your colleagues know about it so that they can get informed about these opportunities as well. Okay, so I think it's always nice to put a face with the voice that you'll be hearing. And so for your information, here are our presenters. A very nice slate of people who are going to share their work with us. And with that, I'll turn it over to Joellen.
There you go, Joellen.
So I thought Okay, can everyone see the slides?
Not yet, but it's still loading.
Okay. So first, well, I'll wait till you can see something. Let me know, Jim, when you see something, or John.
Did it ask you if you have a multiple? There we go. Is it coming now? Sorry. There we are.
Now, all I have to do is, there we go. Okay, great. So everyone can see now?
Yep.
So first of all, I'm delighted to be here. Thank you for inviting me. My presentation is about a new unit called Toward High School Biology and how it illustrates NGSS three-dimensional learning across physical and life science. In addition to the slides, the webinar resources include published studies on the unit and a brochure overviewing the unit's key features. Toward High School Biology is a new middle school unit developed by AAAS and BSCS with funds from the U.S. Department of Education that was designed to support NGS 3D teaching and learning, tested for classroom feasibility in diverse settings, and showed significant learning gains for a demographically diverse range of students. It will be available from NSTA Press this July. The overarching goal of the Toward High School Biology unit is to help students make sense of phenomena related to plant and animal growth using NGSS core ideas about chemical reactions in physical and life science, the cross-cutting concept of matter conservation, and science practices of data analysis, modeling, explanation, and communication. The unit's design draws on learning theory and empirical studies to support NGSS by organizing the unit around a coherent content storyline of science ideas that are made explicit to students, starting instruction from observations of interesting phenomena that are relevant to the science ideas and illustrate their explanatory power, modeling underlying molecular events, and scaffolding explanation tasks. I only have time to show you some examples of the first three principles, but you can see examples of scaffolding explanation tasks in the papers. The content storyline, don't freak out, you can see a big version in one of the papers, shows the conceptual progression of science ideas developed in the 8-week unit. Text in the white boxes at the bottom show the science ideas targeted in Chapter 1, and in essence, the overarching idea is that new substances are produced in chemical reactions because atoms that make up the molecules of starting substances rearrange to form molecules of ending substances. Text in gray boxes show the science ideas targeted in Chapter 2. Again, the overarching idea here is that the mass is conserved in chemical reactions because atoms aren't created or destroyed, but if measured mass changes, it's because atoms have entered or left the system. Text in green boxes show the science ideas about chemical reactions that allow students to make sense of plant growth, and text in blue boxes show the science ideas about chemical reactions that allow students to make sense of animal growth. This slide introduces the instructional approach we use to achieve NGSS 3D learning. For each science idea, students observe phenomena involving changes in matter at the macroscopic level, such as the production of substances that have different properties than the starting substances, or examples of plants growing or animals growing. They relate differences in the properties of the starting versus the ending substances to differences in their molecular composition, which raises the question of how molecular composition could change. They model how product molecules could be produced from reactant molecules. They count the number of each type of atom in reactants and products and discover that they're always the same. And they connect the examples they've observed to the general principles stated in science ideas, which make up the content storyline map. Finally, they use evidence, science ideas, and modeling to substantiate a claim about other related phenomena. So after getting these general instructional principles down, we set about identifying phenomena that would be generative of each science idea, modeling activities that could help students think about what was happening at the molecular level, and tasks to help students generalize principles across the phenomena they observe and to explain new phenomena. So this slide, again, you can look at it later, lists the phenomena that survived all of our classroom testing. As I show you examples from the unit, I'll provide a bit of commentary about why we selected these in particular. Let's look at a few examples, starting with Chapter 1. So this photo actually illustrates two different phenomena that students observe firsthand. First, that a new substance, orange solid, forms when iron is exposed to oxygen in the air. And the second, which they observe over 2 weeks, more and more rust forms as more and more iron disappears. So it gives them an idea that actually the stuff you're making could come from the stuff that you started with. The iron rusting reaction allows students to observe the production of a new substance and the disappearance of both reactants. Students observe a splint test, which is a measure of oxygen, and they can see that the splint test is positive at the beginning and negative at the end. The other thing about this one is that it's a gaseous reactant, and that it can increase the measured mass of a system, and that's going to be important later for plant growth. Students observe or measure properties of starting and ending substances and record the data in a table. They then observe Lego models and the chemical formulas of starting substances, iron and oxygen, and Lego models of ending substance, iron oxide. They relate the differences in properties of the substances to differences in their molecular composition. Students then model the reaction. They build the Lego models of the reactants, iron and oxygen, and then they close their kits and use just those bricks to build models of the product iron oxide. They follow the same process for the reaction between baking soda and vinegar, which produces carbon dioxide gas, water, and sodium acetate. From these two examples, students can generalize the idea that new substances form during chemical reactions because atoms of molecules of the starting substances rearrange to form the molecules of the ending substances or products. Students are then presented with a science idea that states this generalization and makes the point that scientists have observed many more examples than the few they've examined, and that the numerous examples give us all confidence in the generalization, and that because of this, students can and should continue to use it in justifying claims about other phenomena. As each science idea in the content storyline unfolds, the teacher posts a poster-sized copy on the wall. Students then can look at the idea and reference it whenever they're writing explanations. After observing and modeling reactions involving small molecules, students are ready for macromolecules. They watch a video of nylon formation and observe that when two immiscible liquids are layered, nylon thread can be spooled from the interface. And as more and more nylon forms, the amount of both liquids decrease. This is perhaps the most direct evidence that the nylon actually comes from the liquids you start with. So why did we select nylon formation? It's not just that it's cool for students to observe, it's that pretty much all of biological growth involves polymer formation. So nylon formation provides a starting point for familiarizing students with polymer formation that can bridge to the formation of complex carbohydrates and proteins that plants and animals use to build body structures for growth and repair. Students then model the chemical reaction by building ball and stick models of the monomers and then using just those balls and sticks to build a piece of nylon polymer and water molecules. Their modeling activity shows them it is possible to form models of product molecules by disconnecting just a few balls of the reactant molecules and reconnecting them in different ways. In Chapter 2, these same three chemical reactions, iron rusting, reaction of baking soda and vinegar, and nylon formation, are going to be used to develop ideas about conservation and changes in measured mass. So the iron rusting phenomenon, for example, by now students' attention is focused on what's happening to the mass in an open and enclosed system. When iron rusts in a closed container, as you can see here, the mass measured on the scale stays the same. However, when the container is opened, the measured mass increases. Students use Lego models to make sense of what's going on. They actually weigh the baggie before the reaction, react it in a closed system, and weigh the baggie again. And then they can see that when they have to add the additional oxygen molecules to react with the leftover iron, that the mass goes up. So students are now ready to apply these ideas about atom rearrangement and conservation to make sense of plant growth in Chapter 3 and animal growth in Chapter 4. Many students have never noticed plants growing or even observed or paid attention to the fact that when animals grow, they're actually building body structures. So that's where the unit starts here in Chapter 3. So they watch a time-lapse video of corn growing. They consider what new body structures are being made and examine data that provides evidence that corn plants increase in mass as they grow. Data shows that plant body structures are mostly carbohydrates. So plants must make carbohydrates if they're going to build body structures to grow. This provides the rationale for focusing on carbohydrates for the rest of Chapter 3. Students then examine the properties of three carbohydrates, glucose, cellulose, and starch, and consider which of these could give celery its stringiness. Obviously something that has low solubility in water and forms fibers. Students examine the molecular structures of glucose and cellulose, and they notice that cellulose appears to be made up of glucose monomers. Aha, just like the nylon. From here, the question becomes, where do plants get the glucose they need to build the cellulose? For this, we turn to data from experiments using labeled atoms, which is how scientists figured out pretty much all the metabolic pathways and the chemical reactions involved. This shows the data that students examine over 2 lessons. The first provides evidence that the carbon atoms that end up in glucose come from carbon dioxide. The second experiment provides evidence that the oxygen atoms from water end up in molecular oxygen, and hence that the oxygen atoms in glucose must have come from carbon dioxide. And when they model it, they're using yellow sticky on the black carbon atoms so they can actually keep track of what happens. But making glucose is just the first step. This doesn't get us to growth. We've got to build cellulose. So for this, we found an experiment, a published experiment, on an herbicide. And they gave the plants radioactive glucose. The plants took it up. And in the experiment with the herbicide, very little cellulose was made. But in the control, this is where the interesting part from our perspective comes from. In the control, they make lots of radioactive cellulose. Again, students model in both cases. They observe the models. They see where the yellow sticky is. And then they build the models of the products from the reactant molecules. Finally, after they've been introduced to the science ideas and provided evidence from their own observations, they now get to apply it to explaining some new phenomenon. In this case, why the plant in room 2, which has extra carbon dioxide relative to the plant in room 1, why it's going to grow bigger. And then in the second example, we take them to examine Van Helmont's experiment, the data, and his erroneous conclusion. So they critique his conclusion, and then they write a better conclusion and provide evidence. I will skip the animal growth slides, but it's basically the same type of story. And I'll conclude with a final slide that summarizes the strategies that the unit uses to help students make connections across physical and life science phenomena. First and foremost, by teaching both physical and life science ideas about chemical reactions and conservation in the same unit by the same teacher. The second is taking a same instructional approach, that is, starting from macroscopic phenomena and then moving to underlying molecular events. Next, providing data on the same kinds of properties. So students are starting to see the pattern of solubility and whether something forms fibers. And using the same kinds of models and modeling tasks of atom rearrangement and conservation during polymer formation. Another thing we do is use the same language for the science ideas. So for example, the idea of changes in measured mass occur when atoms enter or leave the system. We use that in the physical science ideas, and we use that for plant growth and animal growth. And finally, we engage students in identifying the similarities across physical and life science phenomena and ideas. So for example, the unit starts by asking students to compare nylon formation and a spider spinning a web. And later students are asked how a growing plant is like iron rusting. So that's it for now. I look forward to your questions. Now?
Thank you, Joan. That was a great example. And so I know we'll have some questions when we get to that.
So Jim, you should now see the share my screen button, and you can go right ahead.
Okay. So let's see here. Okay, does everybody see that okay?
Yep.
All right. So my name is Jim Kessler, and I manage a little office in the Education Division at the American Chemical Society. It's called the Office of K-8 Science. So we produce resources for teachers and students from kindergarten through 8th grade. And this presentation today is about a middle school resource that we have called middleschoolchemistry.com, and how we tried to develop the lessons to align to the NGSS. So let's see. Now, when we were producing middleschoolchemistry.com, when we were writing the lessons and developing it, we actually were using the frameworks as a guide because the standards themselves were not out yet. But then when the standards were published, we sort of adjusted lessons and wrote new lessons and tried to align as best we could with the standards because they were a little more challenging maybe to interpret than the information that was laid out in the frameworks. So you can see here I tried to do a somewhat humorous sort of presentation here that they were kind of scary and a bit confusing, the standards, when you first look at them. So I'm sure you guys know about the performance expectations and the information in the boxes here from the frameworks. But just really quick, when we looked at the standards and we're trying to figure out how we could develop lessons to get to the ideas and the performance expectations, we had to decide where our focus would be. So let's just look at this one really quick. MSPS 1.4 was to develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. So that's sort of a, it's kind of a mouthful. It's a lot to take in. But if you look down at the foundation boxes here, you get some information about what from here, what from science and engineering practices, disciplinary core ideas, and cross-cutting concepts was used to create this performance expectation. So we ended up focusing on the disciplinary core ideas. That's really what we wanted to get at, was what is the science content that kids are supposed to be able to demonstrate at the end of a grade band. And then, of course, we would need to write a lesson that had the science and engineering practices and the cross-cutting concepts integrated. But this was our focus. So we really started here. So to look at that particular performance expectation, I thought we could use that as a sort of a starting point to organize the whole presentation and to show you like our thinking process and what we did. So you get information here in this disciplinary core ideas box about what from here went into the performance expectation in these little parentheses after a statement. Like this says MSPS 1.4, so this idea that gases and liquids are made of molecules or inert atoms that are moving about relative to each other. Or in a liquid, the molecules are constantly in contact with others. In a gas, they're widely spaced. In a solid, atoms are closely spaced and may vibrate in position. And down here, the changes of state that occur with variations in temperature and pressure can be described and predicted using these models of matter. So it seems like what they were getting at in this particular performance expectation is what are the atoms like in solids, liquids, and gases, and what happens if you add or remove energy. So we had to start thinking of how to present a set of activities or lessons that would get at those ideas and also include the science and engineering practices and the cross-cutting concepts. So we looked closely at the frameworks, and you can find these in the standards too. There's an Appendix F in the NGSS. It talks about if you're going to use science and engineering practices to get at a disciplinary core idea, the context is phenomena. And Joellen talked about that too. So asking a question, planning and carrying out investigations, developing and using models, constructing explanations, all those science practices use phenomena as sort of the context. So that's what we needed to do. And we knew that anyway, that would be our approach. But it's aligned well with the standards. So what did we do when we tried to develop a lesson? We wanted kids to use science and engineering practices to investigate a phenomena in order to understand and explain a core idea and a cross-cutting concept. Our cross-cutting concepts are almost always have to do with that a microscopic or submicroscopic explanation can be used to show a macroscopic observation or to explain a macroscopic phenomena. That comes up a lot in cross-cutting concepts in this context of trying to explain phenomena using basic chemistry ideas. So what we came up with was a resource, middleschoolchemistry.com, and it's all free. It's called .com, just we grabbed that so nobody else would get it. And that particular performance expectation that we looked at, MSPS 1.4, we sort of tackle that one mostly in chapters 1 and 2. So I thought we could take a quick look at middle school chemistry just for a minute to show you what it looks like, and then I'll come back. So I'm going to escape from here and go to, now we're looking at the site itself, and if you go in through View the Lessons, that takes you to a page where you have a number of chapters. These are all different chapters in the site. We're just going to look at chapters 1 and 2 just very briefly. And I'll go to one lesson that starts the whole middleschoolchemistry.com off, which is Molecules Matter. It's chapter 1, lesson 1. And in the beginning of a lesson, we always have a short video for the teacher so you can see the general focus of the lesson, the key concepts, the main ideas behind the activities, a little bit of video of the activity itself. But let me show you it's always done in a 5E format where we have engage and explore and explain is here somewhere, explain. And we always, I guess I'll do the other two E's, extend, and there's an evaluate, but the evaluate is very sort of a formative kind of a thing where kids use an activity sheet to write down their observations, to answer questions, to maybe make drawings, or to write captions for drawings. So what we're going to look at just really quickly is, so this performance expectation seems to be about what are the particles like in solids, liquids, and gases. So in the engage, we talk to the students about what is matter anyway? Like, what is the matter in your classroom? What are some examples? And kids usually talk about a desk or a book. And then we ask, is a liquid matter? And they say, yeah, maybe. And we talk about that. And is the air in the room matter? So then we finally decide, let's look at a liquid. Let's look at water. It's so universal. Let's check that out first. So let me pop back to the, I'm going to go back to the PowerPoint and show you how we do a little investigation, very short explore, where kids take some water and they put it on a piece of cardstock that's covered with wax paper, and we just tilt it and observe it. And the idea is for the teacher to get kids to look at water in a way they've never looked at it before, to try to understand some things about it. So we asked, does it stay together? Does it come apart? Well, it stayed together, but let's see if we can get it apart. So we're going to try to separate it into two, more or less equal-sized pieces or drops of water. It's not so easy to do, but there we go. So the water's in two drops, but it was difficult, and now we try to bring them together to see what happens if you bring them together. And they come together much, much more easily than it was much easier to bring them together than it was to take them apart. So the question that we ask students is, so what does that tell you? If water is made out of tiny, tiny little particles, let's assume it is, are they attracted to each other? Do they repel each other? Are they neutral about each other? So kids should say, oh, they seem like they're attracted to each other. So then we, in that same lesson, 1.1, we do one other quick phenomena, one other observation the kids can make. It's just a classic, you put one drop of food coloring in water, and we just watch for a minute or two to see what happens. And you would ask kids, what do you see? Did the drop stay at the top? Did it just fall to the bottom? Did it all stay together? Is it spreading? So it is spreading apart. So we ask, well, what could possibly be doing that? And that's not an easy question. So we present the idea that even though the particles are attracted to each other, like we saw in the drop, they're actually moving, believe it or not. So that's not that easy to accept. So let me go back to the website for a second. And let's just look at a model. So every time kids look at phenomena in middleschoolchemistry.com, we try to explain it on the molecular level by showing either illustrations or animations, have kids draw. So in this case, we're trying to show kids that here's a model of water, that if water or any liquid is made up of particles, they're in motion, but they're attracted to each other. They're kind of close together. They don't just spread out like crazy. They go past each other. It looks like they bump into each other a lot. So if you could imagine putting some food coloring in here, if that was made out of little, let's say, dark blue spheres, you could imagine that they would get all bounced around and it would eventually intermix. So this is the approach in almost every lesson in middleschoolchemistry.com, is to get kids to observe a phenomena and to try to explain it on the molecular level through looking at animations and drawings. And let's see. Right. So this PE that we were looking at, the performance expectation, had to do with the particles of solids, liquids, and gases. We're looking at liquids now. But I don't know if you remember, but it included state changes. Now, we obviously can't cover all this stuff in 1 or 2 lessons, but we tried to lay a foundation for this idea that substances are made up of particles, and that if you heat them or cool them, you could something happens. So we asked kids. They saw that in room temperature water that the food coloring was in motion. It moved, and we're claiming that was because of the particles. So we asked them, how could you make those particles move faster? And some kids will say stir it or shake it, but some kids may say heating it. And we ask for examples of why they might think that, and then we try to help them come up with an experiment to show that. So sometimes through guiding questions, kids come up with this idea that let's take cold water and hot water and put food coloring in it and see what happens. So let's do that. If we take, in this case, yellow and blue food coloring and put it in hot water and in cold water and just see what happens. So now we're getting this, it's very clear that the food coloring moves faster and spreads out more in the hot water than in the cold. And we ask kids, why would that happen? Well, if they accept that particles are in motion, it seems like if you heat them, they move faster. The evidence is pretty clear that that's the case. So let me just leave here for a second and pop back to the website, and I'll show you this animation. If I go to Molecules in Motion, which is Chapter 1, Lesson 2, we try to explain what's happening in this particular experiment by seeing that if you have particles are moving in a liquid when they're cold, or it should actually probably say room temperature, and then you heat them up, they move faster, and let's cool them down, and they move slower. In both cases, though, they're attracted to each other and they move past each other. But we're laying a foundation for this idea that, okay, if you heat and cool a substance, in this case a liquid, the particles move faster if you heat them and slower if you cool them. In fact, I don't know if you can see this, but if you heat them, they move faster, and they actually get a little further apart. You can see a bit more blue space behind them. And that's important for this idea that eventually if you heat them enough, they'll evaporate or boil, depending on what you're doing. So this is all in Chapter 1 in the very beginning. So it's kind of, like I said, laying a foundation for what can come later. And then we do something similar with a gas and a solid. We show the phenomena and then animations so the kids can see that the same kind of rules apply, that solids and gases are also made of particles that are affected by heating and cooling. So let me pop out of here and back to the PowerPoint, and then I can finish up. I'm not sure how I'm doing with time. So basically, our question about what we should focus on and how we should write lessons to try to align with NGSS is kind of answered by having students use science and engineering practices to investigate phenomena in order to understand core ideas and cross-cutting concepts. And we do that consistently throughout middleschoolchemistry.com in the way that I showed, very much a lot faster than you would do with students. I think that's it for me. Yes.
Okay, thank you very much.
You're welcome.
Thank you very much, Jim.
Just need a second to get this slide queued up, and then we'll be ready to continue.
Great. In the meantime, can everyone hear me okay?
Yep.
I sounded a little echoey. Oh, now I don't.
Nope, wrong. A little too far. Sorry. It's hard to see the titles on this thing.
That's close.
Yep, getting close. Just
No, back up.
there we go.
There we go.
Sorry about that. Take it away, Aleeza.
All right. Hi, everyone. I'm happy to be here. Thanks so much for having me. And so, yeah, let's just get started. I'm Aleeza Oshry with HHMI's Education Media Group. And today I'm going to share with you implementing NGSS with Systems Connect. So Systems Connect is a merging of efforts of UC Berkeley's Museum of Paleontology project, Understanding Global Change, and my work with environmental literacy standards, which started in Maryland as the Environmental Literacy Partnership in response to a graduation requirement and expanded to a national effort of education stakeholders across the country, informing revision of curriculum in response to changing standards and new education initiatives. So for this presentation, I'm going to focus on one of the resources in the Systems Connect suite of resources, the Planning Guide, for using a systems approach for curriculum and instruction to implement NGSS. So why a Systems Planning Guide for NGSS implementation? The Planning Guide we developed directs the flow of instruction for building conceptual links between topics in a unit or a curriculum while integrating real-world investigations in action. And as every state, district, school, classroom, and educator has their own resources, curriculum, priorities, and local context to consider, a broadly applicable and flexible model is essential for guiding large-scale and systemic implementation. A model that's flexible and adaptable for any setting or subject area ensures relevancy and responsiveness to academic standards while providing inquiry-based investigations that incorporate authentic research and data. So how does the Planning Guide accomplish this? Through the careful vetting of resources guided by NGSS, transdisciplinary practices, and organizational charts embedded in the guide, to establish a learning progression that explicitly builds the conceptual links between topics so students develop a deeper, more comprehensive understanding of our planet's systems and processes. And as the far side comic here illustrates, hopefully avoiding what Larry here has done to the Grand Canyon. So the building of these conceptual links, which illustrate the interconnectedness of topics that regulate our planet's systems and processes, is what we call systems thinking. And this is a unifying approach of Systems Connect. Systems Connect includes a suite of resources, as I mentioned before, developed around UC Berkeley's Understanding Global Change project and informed by the integration and implementation of environmental literacy initiatives and new science standards, which are being adopted around the country. And these components include a framework for teaching global change topics, conceptual modeling for building an understanding of those topics, and a systems planning guide for developing and revising learning progressions responsive to NGSS. So for this presentation, as I mentioned, I'm just going to focus on that last resource, the Systems Planning Guide, to demonstrate how it can be used in both planning for and in guiding the instruction of NGSS-aligned curriculum. A broadly applicable and guided approach for planning curriculum and instruction around new academic standards is critical for implementation success. Curriculum and assessment differs in every school district, even in every school, so adaptability and ability to build in relevancy is really important for maximal adoption and ease of use by educators. These needs are what inform the creation of the three components of the planning guide seen here. Curriculum anchor, which is responsive to academic standards and learning outcomes, identifying where activities and inquiry-based investigations would connect to curriculum topics, the issues investigation, which informs how students would be exploring those topics and incorporates authentic research and data into learning progressions, and the civic action component, which allows for the development of what students would be doing with the information from their investigations. So in other words, this is a guide for developing a scope and sequence for curriculum that enables students to deepen their understanding of content via investigation and building conceptual links between those topics while providing opportunities for application of that information. Before going through the planning guide in detail, I wanted just to highlight a few connections between the planning guide and the NRC's framework for K-12 science education, which corroborates this approach and details the importance of how a deep understanding of topics and content is important for academic proficiency. And although it's the backbone of NGSS, the NRC's stated learning goals and outcomes are really relevant for all subject areas and emphasize contextual, integrated, and connected learning of content in the service of making sense of real-life problems, issues, challenges, or phenomenon. Investigations are an integral part of this model, which provides students with the hands-on experiences and practice with analyzing and interpreting data, resulting in information that students can actually use. Here I put a resource from the Pacific Education Institute, which is available for free and downloadable online. I highly recommend using it for ideas about outdoor investigation. And as the NRC states, students would use these investigations to generate and interpret evidence and develop explanations of the natural world. An experience with investigations to generate evidence is really important for students to be able to tackle issues that currently confront society. Proficiency in a subject area is linked to a deeper understanding of topics and the conceptual links between those topics to be able to communicate and apply that information in designing solutions and problem solving. And to circle back again to the importance of integration, the integration of these experiences is really essential to support development of proficiency and deeper understanding in place of discrete activities that are not explicitly connected. You might be familiar with some of the examples listed here of resources that support this kind of integration. So rather than information being dispelled through individual activities relying on students to make the connections, if we are intentional and explicit about those connections, we can foster deeper understanding and build conceptual links between these topics, which results in fundamental knowledge about how Earth systems work. And we know that educators use a variety of resources and activities in addition to whatever curriculum they might have. And these are just a handful of resources we've been using with Systems Connect. On their own, these are discrete resources, but a planning guide helps to vet and organize these resources into a learning progression aligned with curriculum that gets at the student outcomes that we're looking to achieve, and also directly connected and responsive to NGSS. So let's dive into the planning guide. As a reminder, the planning guide includes these three components: the academic connections via anchoring to curriculum, exploration through inquiry and investigation, and application of information to take informed action. And a little bit of a deeper dive, these components are comprised of subcategories, shown here in this graphic, to direct the curricular and instructional planning. I'm going to go through this in more detail in the next few slides, and then I'll share two examples of how this works in practice. This first section of the planning guide, and I know there's a lot of words here, I'm just going to highlight a few things about academic connections. At the top of this section are where learning outcomes and academic standards associated with a disciplinary topic are detailed. The essential or driving question is a connecting statement that drives the inquiry and connects the resources and activities used in the unit. The yellow column on the left includes blended instructional practices taken from the NGSS science and engineering practices and cross-cutting concepts, as well as other relevant and related disciplinary practices such as the C3 framework for social studies and Common Core. These practice prompts help guide the selection of activities along with this chart shown in the middle of the page, which helps to vet resources by detailing the information available in the resource and the connection to the topic, initiating the building of conceptual links and establishing questions for further investigation. This next section builds the investigation and exploration of the topic. Resources and activities would be selected that will have students measuring variables in the system of study, which affords students the opportunity to identify and continue to build on that interconnectedness of topics. This section also provides the structure for organizing and defining the scope and sequence of activities. And again, that left colored column refers to the transdisciplinary practices that selected resources and activities would be responsive to, such as establishing relationships between variables, making predictions, establishing data collection protocols and data authenticity, analyzing and interpreting the information, and constructing evidence-based explanations. And this last section, students will develop a claim about causes of changes in topics they explored in their investigation activities based on their collected evidence and design a solution which addresses those changes. Resources here in the chart would demonstrate current research, solutions, or action that can be cited by students and referenced for their own work and communication about their own ideas. Again, the left column refers to transdisciplinary practices that selected resources would be responsive to, such as developing evidence-based claims from investigations, designing a solution, modeling a theory, etc. So that you can see the planning guide in action, I have two examples I'm going to just share quickly with you from the Museum of Paleontology and HHMI's Biointeractive. And here you see pictures of teachers participating in UCMP's professional development workshops, working through the activities for the unit compiled with the Understanding Global Change resources to answer the driving question, will parts of the San Francisco Bay Area be underwater in the next 100 years? And a variety of resources were used to develop this unit. And the organization of those resources are detailed here in the planning guide. Just to highlight a few things in this section, because I know there's a lot of information here, but the academic connections made are, which you see at the top, are the NGSS performance expectations for Earth and Space Science across grade levels. And the resources that were selected and listed in this guide were selected in part because of their adaptability to differentiated instruction. So to answer the driving question, water resources from NOAA were selected to establish the context and conceptualize Earth systems functions. And many questions could be elicited from these resources for further investigation. One such question would be, how does water get into and out of the ocean? And moving on to the next section, resources selected for exploration and further investigation of the topic include Cal Academy resources exploring how changing temperatures cause the water cycle, including melting of snow and ice cover, resources from UC Berkeley and NASA exploring global climate change, and experiments to understand thermal expansion of water from the University of Central Florida. From these resources, students will be collecting and analyzing data and answering investigative questions to construct explanations about the driving question as detailed in this chart. And in this last section of the planning guide, students will be reviewing current and local data regarding sea level rise, including satellite data and press coverage from a variety of stakeholders in order to develop a claim based on their own investigative evidence and design an actionable and implementable solution. In this second example, I created a unit of study around ecosystem impact using resources from HHMI's Biointeractive to study how ecosystems are impacted in changing environments. The academic connections made here to NGSS life science disciplinary core ideas for high school, and to establish the context and conceptualize Earth systems functions and changes across large and small timescales, I selected two interactive apps from Biointeractive's website. Again, many questions could be elicited from these resources for further investigation. One such question would be, how are changes in the past similar or different than more recent changes? And moving on to the next section, resources selected for exploration and further investigation of the topic include Biointeractive's activities, exploring ecological relationships, food webs, how disturbance in a system can affect species interactions, etc. From these resources, students will be collecting and analyzing data and answering investigative questions to construct explanations about the driving question. And in this last section of the planning guide, to provide a case study of current research and mitigation, students will be reviewing one of the world's largest restoration and conservation efforts happening in Gorongosa National Park in Mozambique, Africa, which includes community and stakeholder involvement and perspectives. And then students would conclude the unit with developing their own claims based on their own investigative evidence and design an actionable and implementable solution for a local or regional situation. And explicitly demonstrating the connection and links between topics can also be accomplished visually with conceptual mapping or storyboarding, which is another resource we use with the Systems Planning Guide in Systems Connect as one of the resources I mentioned earlier. As you can see here, this is a workshop we led with teachers in February. So a guide for integrating resources into a learning progression that explicitly builds the conceptual links between topics so students develop a deeper, more comprehensive understanding of our planet's systems and processes, enables students to use these activities to develop evidence-based explanations of the natural world, which then define a curricular scope and sequence for instruction, student learning engagement, construct relevant conceptual links and relationships between topics, and provides a roadmap for NGSS implementation. So Jessica Bean from UC Berkeley is also on the webinar today, and here's both of our contact information. She's my colleague at UCMP and is the brains behind the Understanding Global Change project. So if you have any further questions for either of us about any of the resources that I mentioned here today, or would like copies of the units that we built out, feel free to contact us. And that's it for my slides.
Great, thank you, Aleeza. So everybody on the call, it's a great time to write some questions into the chat box if you have some. In the meantime, I'm wondering, where can people, Aleeza, where can people find planning guide, or where will it be at some point? Aleeza, you might be.
I'm sorry, was that question directed at me?
Yes. There's a question. Where can we find the planning guide?
Oh, yes. So the planning guides are not yet available online. Although they will be, along with other resources that will be available on a website that's currently being developed for Understanding Global Change. But if you contact either myself or Jessica, we can share the planning guide as a PDF document with you and discuss further any application or questions that you might have.
Okay, great. And I think there's a lot of questions, a lot of similar questions. Where can we find units that Ellen described? How can people get a hold of the units that you just described, Aleeza? And I think it's a good idea to add those URLs to the email that goes out when we have the webinar archive link. So for all the presenters, I would say either put them in the chat or send them to us so that we can get them out to this list. There's some other questions. Christine is wondering if Aleeza has any resources for elementary.
So I'll just answer that quickly in terms of the application of the planning guide can be used for any grade level with any resource. So the beauty of these tools is that it can be used with any curriculum, any resource, any grade level. It's an organizational tool for building conceptual links for topics, and it can use resources from supplemental providers, other organizations, from your own curriculum. It's a guide for organizing the learning progressions.
Mm-hmm. Okay. Barney Brower has a scary question for Ellen. That asks, what's the next content area that Project 2061 will be addressing after THSC is launched? Is there a plan for what?
Sure. So we're currently working on an energy unit across physical and life science for high school. I'll say biology. That's where we're doing our testing. So right now we're in the pilot test stages, and we'll be field testing this coming fall, and then hope to have it available the following year. We're also partnering with some others who are the Genetic Science Learning Center, working on an evolution unit that integrates science practices and ideas about heredity and mathematics as well. So the grand plan is our 8th grade unit took us 5 years. We can't do this alone. We are not getting into the materials development business. We need to work with other people, and so we're quite willing to collaborate with those who are like-minded.
Great. And do any of the presenters have an answer for Kanatan? How can we measure carbon in soil? Did anybody address that in their units? And if the answer is no, Kanon, then let's follow up so that my group can help you with that. Any thoughts on that?
I do not have anything in middleschoolchemistry.com.
Okay. So, Kanon, I'm going to put my email in the chat there, and if you reach out to me, then we'll help you with that offline. So with that, it's 3 o'clock. I want to thank all of our presenters for 3 o'clock my time. I don't know where it is, where you are. But I want to thank all of our presenters for sharing the work that they've been doing and adding to this discussion. I'd like to draw your attention again to the upcoming webinar. Even though this is the end for the academic year, we do have another webinar scheduled on September 14th coming up. These are always on the second Thursday at 1 o'clock Pacific time, 4 o'clock Eastern time. So since you signed up for this, I believe you get notice of that. I'm just drawing your attention to that. So thank you for all of your contributions here. And there's a couple more questions in the chat. And Jessica, we don't typically email a certificate of completion, but if you'd like one, if anybody would like one, please let me know and I can figure something out. And
So I can respond to Christine.
Oh, great.
So there are formative assessments for each chapter, and there are online resources that will be published with the unit that include scoring rubrics, things like that. We have our own that we've used for research purposes, multiple choice and constructed response pre and post test, and we're trying to figure out whether we should make that available, and if so, how.
Okay, very good. All right. Well, thank you, everybody. Jessica, we'll get back to you about the certificate. We've got a couple of options here, but my email is in there for you to connect with us on that. And thank you again, everybody, and have a great rest of your day.
Thanks a lot.
Thank you.
Thank you.
Thanks, everyone.